We want to continue our discussion of covalent bonding and move on to some slightly more advanced topics and talk a little bit about the shapes of molecules. The theory that we're going to use, the model that we're going to use to explain how molecules get their shape, what causes them to have certain shapes, is called VSEPR, Valence Shell Electron Pair Repulsion Model. And all that does is assume that each of the groups of electrons that are around a central atom will repel each other and get as far apart as possible. So if we want to know the shape of a molecule that has one central atom, the first step in that process is to draw the Lewis structure of that molecule and then identify which atom's shape we are most interested in. That's going to be the central atom in a molecule that has one central atom. Then we want to count the number of what your author calls electron charge clouds around that central atom. A charge cloud is any group of electrons, so a single bond counts as one charge cloud. A double bond counts as one charge cloud. And a triple bond counts as one charge cloud. A lone pair also counts as one charge cloud. And so if we count all of those charge clouds up and then look at how many of those charge clouds are bonds to other atoms and how many of them are lone pairs, we can predict the shape that molecule is going to have. In fact, a list of the shapes and the number of charge clouds associated with them that you should familiarize yourself with and be ready to reproduce on the test is found on page 268 in your textbook. So you want to take a look at that, and we worked through this in lab this week already, and the kinds of work that you did in lab will be good preparation for these kinds of test questions. We go on to a little bit higher level theory, and we have a theory that explains bonding called valence bond theory. The idea is that covalent bonds are formed by the overlap of atomic orbitals, each of which has one electron of opposite spin. In order for the orbitals to overlap, they must be in the same phase. That means basically an orbital, we draw it as a plot of a graph, but it's actually a function. And that function has a positive side and a negative side to it, and we calculate the probability of finding the electron in a particular space by squaring the function. So we get a positive number for probability regardless of whether the wave is in a negative or positive phase. But in order for two orbitals to overlap efficiently, either both sides have to be the positive phase or both sides have to be the negative phase. And that will get us an explanation for a lot of different kinds of single bonding, but not all. In the early parts of this theory, each of the bonded atoms maintains its own atomic orbitals. So we just saw two p orbitals overlapping to make a fluorine molecule in the previous slide. The electron pair in the overlapping orbitals is shared by both atoms. So the greater the amount of orbital overlap, the stronger the bond is. And when we're looking at p or d orbitals, they have a certain direction to them. So the direction becomes specified by the orbitals. And VSEPR that we just learned, that we just talked about, becomes a problem when we look at this because p orbitals are at 90 degrees to one another. And so the 2p orbitals and perhaps the 2s would be the ones involved in bonding for a carbon atom if we're making CH4. But the bond angles we just talked about come out to be 109 degrees if you look at the shapes that are caused by having four charge clouds around a central atom like we would in CH4. But the orbitals are at 90 degrees to one another. So this portion of valence bond theory no longer works to explain geometries for certain sized molecules. And so what we have to consider is the idea perhaps that each p orbital is no longer a p orbital and the s orbital is no longer an s orbital, but that 2s and the 3 orbitals that we call 2p, the one on the z-axis, the one on the x-axis, and the one on the y-axis, mix together mathematically to form 4 new equal and opposite orbitals. So since each of these is made from 3/4 of a p orbital and a quarter of an s orbital, we'll call, so 3 parts p and 1 part s, we'll call them sp3 orbitals. And if we do that mathematically, the resulting orbitals that we get are 109 degrees apart, and we could bring in the hydrogens to bond with each sp3 orbital, and that gives us a proper mathematical and visual explanation for the bonding in CH4 and other tetrahedral molecules. And here's another visual of that. Now, when there's a double bond, we have a little bit more explaining to do, and the way that we'll explain that is instead of all 3 of the p orbitals hybridizing with the s orbital to make 4 new hybridized orbitals, let's say only 2 of the p orbitals hybridize. Let's say the x and the z orbitals from the 2p hybridize with the s. So we get 3 new orbitals, each of which is 2/3 p behavior or character and 1/3 s. So we'll call those sp2, and that leaves a p orbital on the z-axis here that's unhybridized. If we bring 2 carbon atoms together in that way, we can get direct overlap to make the same kind of single bond we would have made between 2 carbon atoms if they were sp3. But then the p orbital that didn't hybridize on one carbon and the p orbital that didn't hybridize on the other carbon can overlap from side to side. That's going to cause a couple of different things. It'll cause a stronger bond, what we'll call a double bond. But it's also going to keep this bond from being able to rotate. So whatever is on this side of the double bond as opposed to this side has to stay on that side, at least as it relates to what's over here. And so single bonds can rotate readily, just like they did in our plastic model kits, and double bonds cannot, again, just like they didn't in our plastic model kits. If we had sp3 and sp2, we can also have sp hybridization. That would leave 2 unhybridized p orbitals, let's say the z-axis and the y-axis. So the sp orbital ends up along the x-axis. And we bring 2 carbon atoms together and let them bond with one another. We get direct overlap here, and we get side-to-side overlap here to make a second bond, and side-to-side overlap here to make a third bond. And so we have a triple bond. By the way, and this was shown in some of the other pictures, but I'll mention it here, when we get a bond from direct orbital overlap, we call those sigma bonds. And when we get, and here's a Greek letter sigma, lowercase sigma, when we get the side-to-side overlap to make a bond like we do with these p orbitals, we call those pi bonds. Pi bonds are not quite as strong as sigma bonds. Now that brings up an interesting question. If we think about this particular molecule here, C3H4, where the central carbon is sp hybridized and the 2 outer carbons are sp2 hybridized, we get double bonds between each carbon, and then the outer carbons each have 2 hydrogens. And the question is, do we have a planar molecule the way it looks here in 2 dimensions? And we want to go ahead and use orbital theory to explain that. So what I'd like you to do right now is pause the video for a few seconds and think about this and try to draw it out and see whether you think this molecule will be planar or not. And then I'll show you on the next slide how that comes out. Alright, so if that central atom is sp hybridized, that means it has 2 One on this we'll call the z-axis, and one on this we'll call the y-axis, two unhybridized p orbitals. One of them, the one that's along the y-axis, can bond, make a pi bond with this particular carbon. But if that p is on the y-axis, that's going to force the hydrogens to the z-axis. That leaves the z-axis p able to bond with this carbon. That forces these hydrogens to the y-axis. And so we don't get a planar molecule. In fact, the plane created by these three atoms is orthogonal, or 90 degrees perpendicular to the plane created by these three. Valence bond theory does a pretty good job of explaining the properties of a lot of different kinds of molecules, but there are some very simple molecules, as simple as O2, whose properties can't be entirely explained by valence bond theory. And so we need a bit more mathematical, a bit more advanced bonding theory to explain that. And the name of the theory that will do that is molecular orbital theory. It's presented in sections 8.7 through 8.9 of your textbook. They're a little bit beyond the scope of this course. I'd like you to read these sections and think about them. And think about O2 in particular. I'll try to put an extra credit question dealing with those ideas onto this test, or onto the final exam, or possibly on both. So it would be a good idea to at least read through those as you have time over the next week or so. Additionally, there's an interesting topic presented on page 299 through 301 toward the end of this chapter that will be very important in organic chemistry. It's important in biochemistry. Could also make a nice extra credit question for this test or for the final. And so expect one or the other of these topics to present themselves on those tests. And here are the suggested homework problems from Chapter 8. As soon as you get a chance, you want to start taking a look through those and seeing which ones you can complete, which ones you need some help with, and we'll work on those in class.